Okay, let's begin. Um, Hello, everyone. This is Tanya. I'm one of the TAs assigned to the course Aircraft Stability and Control, taught by Professor A.K. Ghosh sir. So we will go over the contents of week 8. Before that, we'll just go over the revision of week 7 and do the few questions that were there in your assignment. So let's begin. Okay. So in week 7, we learned, I think in week 6, we started what is stick-free stability. Stick-free is when you let the elevator float freely. Okay, till then you had your elevator fixed at some location, at some angle, and then there was a force applied by the pilot to keep it at that angle. All right. So after that, we saw that if you let it float freely, there is a hinge moment. There is a hinge moment where, so this is your tail, horizontal tail. This is your elevator. So this is the point where it's hinged. And if you let the elevator, even if you don't let the elevator float freely, due to the forces generated at the center of pressure of the elevator, there are forces and moments acting on the hinge. So there's a hinge moment. Okay. This is the hinge point. Hinge moment is given by this equation where CH is a hinge moment coefficient, very similar to the pitching moment coefficient or the lift coefficient also. So that is a similar equation. Then we use the linearized equation of motion, equation for the coefficient of hinge moment, which is given by this equation. And it depends on alpha t, angle of attack at the tail, delta E, elevator deflection, delta T, trim tab deflection. Okay. And now all of these derivatives are there. That is CH alpha tail, CH delta E, and CH delta T. We had discussed in the previous class and the one before that all these three derivatives, the CH alpha tail, CH delta E, CH delta T, they are all negative. That is given by this point, only if the hinge point is ahead of CP. Now, if the hinge point and CP are the same point, then what happens? What happens is that there is no moment at the hinge point because the forces are acting at the hinge point. There is no moment there. It's only when you transfer the forces from a point to another point that you have a moment, right? So if your 2 points, your center of pressure and hinge point are at the same location, then you will have no moment. Okay. So why are these three negative? I'll just go over it briefly. So if this is your tail, this is your elevator, suppose there is a change in angle of attack, del positive change, okay? So now there will be an additional force, delta L, right? Because of the increase in angle of attack, there will be an increase in lift at the tail. Can you just confirm if I'm audible? Am I audible? Thank you. Thank you. Okay. So now because of the increase in angle of attack at the tail, there will be an increase in lift generated at the tail. Now this increase in lift generated at the tail will be at the center of pressure. And since the hinge point is ahead of center of pressure, it will cause a anti-clockwise movement. Anti-clockwise in our convention is nose down. Nose down is negative. So positive alpha tail produces negative moment, hinge moment. It is that. Negative hinge moment. So your CH alpha tail is negative. Now let's look at the delta E case. So if this is your tail, horizontal tail, and this is your elevator. If I deflect it down, it is positive delta E. Positive delta E downward. Right? If I deflect it down, again there is an increase in lift. This increase in lift again produces an anti-clockwise moment at the hinge, which is nose down. Pitch down produces negative hinging moment. Right? Negative hinging. Similarly, when the trim tab is also deflected downwards, that is positive delta T, it gives an increase in lift, which produces a nose down moment at the hinge point. Okay, so again, positive delta T also gives you a negative or anti-clockwise hinge moment. Okay, which is why all of these parameters are 0. We had verified this in a couple of examples that we solved as well. Okay. Now to find out the freely floating elevator's angle. So if you just let the elevator float, to find out at what angle it will stop, what do? It floats when the moments are balanced, right? When the moments are balanced, what happens is sum of all the moments is 0. So your CH, the hinge moment, would be 0. So to find out the angle at which the elevator floats freely, you set your CH to be 0. And for this case, assume your CH not to be 0 and assume that there is no trim tab. Okay, set it to 0 and that angle is given by this equation. Now, see here that it is proportional to the alpha tail, angle of attack at the tail anyways. So now your CH alpha tail, CH delta E, both are negative, right? And you have a negative sign here. So if it is a positive angle of attack at the tail, your freely floating elevator would be a negative angle. And if it is a negative angle of attack, freely floating elevator angle would be positive. You can see that it's pretty intuitive, right? So if this is my horizontal tail and this is my elevator, and if it is subjected to a positive angle of attack, and if the elevator is let to float freely, it will tend to move upwards, right? It will tend to float upwards. And we had seen that upward deflection of the elevator is negative, which is what this relation tells us. So if it is a positive alpha tail, your freely floating elevator would be negative. Similarly, vice versa, right? If it is a negative angle of attack, if the tail is subjected to a negative angle of attack, your elevator will float downwards. All right? Okay. Now this statement, delta E due to alpha tail tries to counter the moment. That is what we just discussed, right? If it is a positive angle of attack, your positive angle of attack we know produces a negative hinge moment. And let me just write that. Positive angle of attack at tail produces negative hinge moment. But positive angle of attack also gives you negative delta E. Also gives negative delta E. But negative delta E, we know it gives you positive hinge moment. So what does this imply? That the delta E deflection due to angle of attack tries to counter the moment, right? This in turn gives you a negative component of hinge moment. Right? Is the statement clear? So if my aircraft is subjected to a positive angle of attack, my elevator will float upwards, as in it will be negative. Now, both of the moments produced by these two deflections or these two changes in angle counter each other. Okay, that is what this statement means. Okay. Then we saw the stability, static margin of the stick free and the stick fixed case, right? So from here we saw that DCM upon DCL is the slope, of the graph between CM and CL. For a stable aircraft, the slope will be positive or negative, this DCM by DCL. For a statically stable aircraft, what will the sign of this quantity be? Negative. Yes, exactly. So our graph will be like this. CM versus CL. Now, if it has to be more stable, should it be more negative or less negative? More negative. Okay. Now, can you look at this equation and tell me if the stick free or stick fixed case, which is more stable? More negative means most stick fixed. Yes, stick fixed is more stable. Exactly. Because your stick fixed DCM upon by DCL, like you said, is negative. And the second term on the right hand side, this is positive, this is positive, these two terms are positive, this entire thing is positive, and the negative sign gets cancelled, and this positive. So the entire second term on the RHS is positive. What it does is that it makes the negative value less negative. That means less stable. So the stick free case has lesser slope than the stick fixed case. Hence, the stick free case is less stable than the stick fixed case. You're absolutely right. Okay. Now let's go to the next. Then we studied some stick conventions about stick force and all of that. So if you push the stick forward, it is implied, the convention is that pushing the stick forward is positive. When you push it forward, it gives you more velocity. Now, if you want more velocity, what do you have to do to maintain the trim conditions? You have to reduce the CL. When you reduce, how do you reduce the CL? By reducing angle of attack at the tail. How do you accomplish that? How do you ensure that you reduce the angle of attack at the tail? By deflecting your elevator down. Why? Let me just show you that. So this is my elevator. I deflect it down. Down is positive. It produces an increase delta L, which produces a negative pitching moment. When it produces negative pitching moment, what does it? It reduces the angle of attack. So delta E down reduces the angle of attack at the tail. Correct? If I deflect my elevator down, positive elevator deflection reduces the angle of attack at the tail. Hence, when you backtrack all of this, these conditions remain valid. Okay. So just remember that pushing the stick forward is considered positive. Then delta E required is governed by the stick fixed static margin. So we had an equation of delta E required, right? Was delta E naught plus d delta E by dCl into CL trim. We had this equation. Now this d delta E upon dCl was what? X bar NP minus X bar CG by Cm delta E. So what this statement says is that this delta E required is governed only by the stick fixed static margin, right? This one, this term, it's not the stick free case, X bar NP prime. It's not X bar NP prime, it's only X bar NP, which is the stick fixed case. Okay. Then we saw some three conditions. So here, I think that we have made a mistake. Just hear me out. So first case was if the delta E float is equal to delta E required. What it means is that if you let your elevator go, that is stick is not fixed, stick is free, elevator is floating, and it is floating at the required elevator deflection. So the pilot does not have to push the stick, does not have to do anything. It is already at the required delta E, not required to put any force. So FS is 0, neutrally stable, fine. So the first statement is clear. Next, if delta E float is less than delta E required, the example that sir gave was if delta E required is 5 and delta E float is 3. So given our convention, what it says is that delta E float, currently it is at 3. So this is 3 degrees. We require it to be at 5 degrees, right? So that means you need to deflect your elevator down. You need to deflect elevator more. So I think that what we have done here, what we've written here is incorrect. So if your delta E float is less than the delta E required, I believe that we should deflect the elevator down. Correct? Just think about it for a minute. I had mentioned this in the last 2 classes, but it just came to me that that did not really make sense, or it was going against. Just try it with a few other angles. I just took 3 and 5 because that's what was discussed in the class. Try it. Let's try it with some negative values. Okay, so if it was just a bit. So if it was this was your horizontal tail, and so it's floating at this angle, delta E float. So this is, let's say, minus 3 degrees, and you require it to float. So minus 3. Suppose it's floating at minus 10 degrees and require it to float at minus 3. This is delta E float. And this is delta E required, right? So here delta E float is less than delta E required, yes. If I need to bring delta E float to delta E required, I need to deflect my elevator down. Hence, I should be pushing the stick and not pulling the stick, right? Did you go through the contents, week 7 contents? I think sir discussed this in week 7 or week 6. I think it was the last lecture of week 6, if I'm not wrong, because I had been, this slide I had put up in the last 2 sessions as well. So week 6 and week 7, I'd put up these slides. So do you remember what sir says? I believe that this is what he said. This is the example, in fact, that he took 3 degrees and 5 degrees. Does anyone remember? Or do you think we're making a mistake? Which one do you think is correct, Yashas? I'm also wondering out loud. So let's just take the second condition. This was first one, second, and third. So for the second condition, when delta E float is less than delta E required, should we deflect the elevator up or down? What do you think? Must be down in second condition, right? Yes. Do you remember what sir said? Either of you, do you remember what sir said? Okay, I think let's just play that lecture. Just give me a minute. Stop the sharing. Okay. Sir's lectures. Can you hear this? Can you see it?
K is minus.
Can you confirm?
This is minus, this is minus, and this is minus, this is this. Now,
Okay, let's just listen to it.
now I will plot here. We will put pull here, AFS. So naturally, this negative say. What the graph is? Now, what is to be inferred from this graph? That if I am flying at this speed, what is the meaning? So it's the speed, push the stick and take V trim to this point, suppose any change from that Fs equal to 0.
I don't think this was the lecture. Just give me a minute.
Stick force, and that is the case in our term through stick force. We say that is a neutral stable case.
Yeah, okay, so this was the first case.
The ability design,
Let me-
that means the stick force applied will be 0, right? Into alpha tail. And suppose the way CH alpha T and CH delta E are designed, that delta E float, when I compute through this, that becomes exactly equal to what is the delta E required by itself by floating. That means the stick force applied will be 0, right? You don't require any stick force.
Okay.
So that is the case where we
So that was the first case, clear, right? So if the delta E float is the delta E required, you don't need to apply any stick force. Stick force required is 0. Okay, now let's go to the next case.
say stick force is 0 physically. That means if the airplane is designed that whenever it goes to a particular CL, automatically the float is exactly equal to what is the delta required. So it do not require to apply any stick force. And that is the case in our term through stick force. We say that is a neutral stable case. That is Fs equal to 0. Okay. This here, again, we are trying to build some convention. Second case will say, if this delta E float is less than delta E naught plus d delta E by dCl trim into CL trim at a given CL. That means, what happens? That means, please understand, suppose delta required was 5 degree, and by float it has come to 3 degree, that means pilot has to increase the elevator up by 2 degrees. So how?
So is that clear? The second case, he says that delta E float is at 3 degrees and delta E required is 5. Let me just go with
3 degree, that means pilot has to increase the elevator up by 2 degrees. So how does he do that? He has to put the elevator up, so he has to pull the stick. Okay? So So he has to pull the stick. You could see here, he has
So, is anybody able to tell me where we went wrong or where it's wrong or anything? Any comments? So, sir just mentioned the second case, the one that we said, where delta E float is 3, delta E required is 5. Right? So, by convention, delta E float is at 3. It is required to go to 5. So, we have to push the elevator down. Okay, so that is what it is by convention. But sir just mentioned that we need to pull. So, do you have any comments on this? Are we going wrong somewhere? Where are we going wrong? Think about it. Where are we going wrong? So delta E float 3, delta E required 5. We require it to go to 5. So it should be elevated down. And if it's elevated down, we need to push the stick forward. So Fs should be greater than 0. Can either of you think of some explanation? Okay, so I will check with the other TAs and get back to you maybe next class. But you also, both of you, all of you, go and check it out. See what is the reasoning behind this, or see what is the correct version. I will check with the other TAs and we'll, I think, figure this out next week. But you must also yourselves go and check this, and we'll have the discussion next week. Okay. So I still believe that it should be elevated down, but we'll discuss this next week. Is that all right? Or do you have any comments on this as of now? Any comments? Let's just have a discussion. Okay, if not, we'll proceed and we'll get back to this next week. Okay, so then we moved ahead with the equations for Fs. Fs is stick force. Stick force is hinge moment into this term. Delta E is elevator deflection. What was Ls? Ls and delta S. Ls, what is Ls? What is Ls? What was Ls? Or delta S in the stick force equation? Ls or delta S, anything, either of those. We discussed this last 2 sessions, and I think there was a question on this. Try to think about delta E. Delta E is the elevator deflection. So what is delta S? So it is some angle, right? You know that. So what angle is it? What delta S? What is it? Delta S or Ls. Ls is some length, right? By name, you can figure that out. What is Ls? What is delta S? Ls or delta S, either of those. So this is the stick is connected to the elevators. Now, if I push the stick, it becomes something like this, right? It becomes something like this. Forgive my drawing. So this length from its hinge point to its tip is Ls. Okay, that is the length of the stick from the hinge point to the end. What is delta S? What is delta S? Can someone tell me what is delta S? What is delta S? LS is the length of the stick, right? So what is delta S? Delta S is just this angle by which it is deflected, correct? Am I audible? I'm not sure. Can you confirm? Can someone just tell me on the chat box if I'm audible? Okay, thank you. Okay, so delta S is the angle by which the stick is deflected and LS is the length of the stick. Okay. Okay, then we moved on to the derivation and we came up with this equation for stick force. All right. Okay. Then this was a question that we discussed last week and we had to do it in a hurry. So I thought we'll do it again. Just go over it quickly. So read the question carefully. It says for an airplane, W by S is 400 Newton per meter square, flying at an altitude of where density is 0.8 kg per meter cube, and the following data is given to you. So they're giving you 3 velocity readings, and each of this is the stick force. Okay, so this is FS1, and this is FS2. So for different velocities and for 2 different CG locations, they've given you stick force readings. Okay, so this is the required, delta V required to fly at this velocity. What was the stick force needed for 2 different CG conditions? Okay, is the data clear? To fly at a required velocity, 3 different required velocities, what was the stick force required for 2 different CG locations? Okay, is the given data clear? Is there some question? Is there some confusion regarding what data is given? Okay, so they've given you the W by S, the wing loading of the aircraft, and they've given you the density at the altitude at which it's flying. Then the data that they've given you is to fly. So 2, stick force of 2 is what is required to fly at velocity of 50 meter per second, right? Now, for a different CG location, CG is 0.25, the stick force required to fly at the same velocity is 1. Similarly, for 2 other velocity readings, you have these 2 cases, right? How much force is required to fly the aircraft at the given velocity for 2 different CG conditions? Is that clear? Yes. Okay. So now let's try to find, the question says, let me erase this. So question says, find the stick free neutral point. How do we go about doing this? This is FS1. This is FS2. How do we go about doing this? This is the data that you have. You have stick force, you have velocity, you have wing loading, you have density. Notice here that they have said, they've given this in the question clearly. Otherwise, push is positive. Okay. In the question, they've mentioned that we need to take pull as positive. Okay. Otherwise, push is positive. Okay. So in this case, if this is pull, so this will be positive. This will be positive. 0 is fine. This will be negative. This will be negative. All right. So how do we go about doing this? How do you find the stick free neutral point? How do you define stick free neutral point? How is stick free neutral point defined? Or let's start with stick fixed. Okay, let me start. Neutral point free. Stick fixed. NP is stick fixed neutral point. NP prime is stick free neutral point. How do you define neutral point? What is the definition of neutral point? What was the definition of neutral point? What was the definition of neutral point? What was the definition of aerodynamic center? Let's start with that then. Aerodynamic center. AC. What was the definition? What is AC? What is aerodynamic center or neutral point? Tell me any one definition. How do you define it? What is neutral point? What is aerodynamic center? What is aerodynamic center? I don't think there is any point in proceeding if we are not able to give a definition for aerodynamic center or neutral point. Please try, please just recall. What was center of pressure? Okay, Suraj, point at which forces concentrate. What is that point? You've given the definition for what point? I have written 4 points here on the board. You've defined which of those? Center of pressure. Perfect. Yeah. What do I say? Location of action of aerodynamic forces. Okay. Now, what is AC? Aerodynamic center. What is aerodynamic center? Eight weeks of classes have completed. You submitted the assignments. It's a very simple definition. Aerodynamic center, I think we started week 1 with aerodynamic center. Point at which lift force acts. So what is the difference between center of pressure and aerodynamic center? This is very strange that you don't recall us doing this. Center of pressure is the location where the aerodynamic forces act. And then you told me that point at which lift force acts is aerodynamic center. So doesn't the lift also come under forces? All the forces act at the center of pressure. What is aerodynamic center? I don't think after 8 weeks you should be saying that you're not sure with your answer. This we had discussed in the very first week. What is aerodynamic center? What is center of pressure? And then we moved on to neutral point. And then now we've reached stick-free neutral point. And now we've started dynamic stability. Please Google it and or refer to your notes or something and tell me what aerodynamic center is. Please Google, please refer your notes, please rewatch the lectures or the slides or anything. Please tell me what aerodynamic center is. You should not at this point be unsure of what aerodynamic center or center of pressure. You should have the clear distinction. You rightly said center of pressure is where the forces act, where all the aerodynamic forces act. Lift, drag, everything. Lift does not act at the aerodynamic center, it acts at the center of pressure. What is the aerodynamic center? Point at which pitching moment is independent of angle of attack. Exactly. What is pitching moment? Since all these questions are confusing, what I'm going to start with the basics again. What is pitching moment? So AC you've defined point at which pitching moment is independent of alpha. Correct. What is pitching moment? Okay, he has left the meeting. Very strange. Can you tell me what pitching moment is? I'll give you about 5 minutes. Try to tell me what pitching moment, neutral point, stick fixed, stick free, aerodynamic center, what is the difference or something. Tell me something about that. Just Google it, refer to your notes or refer to your assignment questions, anything, and try to get back to me. I'll give you about 5 minutes to do this, okay? Because I don't think it's going to make much of sense if we proceed if this is not clear. AC he has described, defined correctly, but then he left the meeting right after it. So just quickly tell me, take about 5 minutes, refer to your notes, tell me of any one of those, right? Any one of those. Pitching moment, AC, CP, neutral point, stick free, stick fixed, anything. Take 5 minutes, do that. Okay, so I don't think anyone has replied, so I'll just go over it. Aerodynamic center is the point at which the pitching moment is independent of angle of attack. What is pitching moment? It should be fairly simple at this stage. It's represented by M. It is a moment happening across the pitching axis. Pitch up, pitch down, nose up. That is the pitching moment. Okay, so when you deflect your elevator down, produces lift, produces a pitch down. Right? What is neutral point? Neutral aerodynamic center was described for a wing, and now neutral point is described for an aircraft. It is the exact same thing. Okay, pitching moment, where the point at which pitching moment is independent of angle of attack. Why did we come up with the aerodynamic center? Because if we use CP for our analysis, then CP is a point that keeps varying throughout the flight. Okay, so it would be very difficult to do our analysis if the point at which you're doing the analysis keeps varying throughout the flight. So we came up with a point called aerodynamic center, where we transfer the lift and drag forces, the aerodynamic forces. When you transfer the forces to a point, it comes with a moment. That is your pitching moment. Okay, so we came up with a point where the pitching moment is independent of angle of attack throughout the flight duration. That is your aerodynamic center for a wing. For neutral, for an aircraft, it is called neutral point. Okay, neutral point is the same thing. AC of aircraft. What is a stick-free neutral point? It's just when the stick is left free. Okay, how do you define these two now? Let me just write this down. Neutral point is when DCM upon DCL, DCM upon DCL is 0, right? It doesn't vary. Now, sir had mentioned, I think in week 3 or 4, how do you find out this neutral point experimentally? How do you do that? You take d delta E upon DCL, the point at which the slope becomes 0, d delta E upon DCL. Okay, so we had plotted the graph, taken the slopes of each CG location, and then put it on another graph and extrapolated it to see where it becomes 0. The point at which the graph becomes 0 or the slope becomes 0 is the neutral point. The CG location at which the slope becomes 0 is your neutral point. Okay. Now, similarly, what is it for stick-free neutral point? What is it for stick-free neutral point? Refer your notes, go over, let me know. For stick fixed, it is d delta E upon DCL, where the point where that slope becomes 0, the CG location where that slope becomes 0 is your neutral point. Now, what is it for stick free? We had discussed the same question the last week. We'll just go over it once. With stick free neutral point, what is the quantity? What slope should become 0? Is it the same? Is it different? What is it? Here it is DCM by DCL. Free should be 0. This is fixed. Here free. Let me write that neatly. This is free. Okay, so that should become 0. But experimentally, how do you find it? What slope should become 0? What is analogous to d delta E upon DCL for the stick free case? What is it for the stick free case? Refer to your notes. We had done this even in the last lecture, so you can just pull up the lecture and see, look at the slides. is DFS by Q by DCL, right? Okay. So how do you go about doing this question? You have to find out the point where DFS by Q by DCL is 0. So what are the terms that you know? You know Fs, right? Can you find out Q? You don't know Q, right? You can find out Q. So for the three cases, first, what is Q? Half rho V square. V we know, rho we know. You can find out Q, right? So let's just make a column for Q. Let's find out Q. Okay, wait. Suppose we find out Q. Next, what do you do next? Tell me what to do next. What do we do next? What is the next unknown term? CL. Exactly, CL. What is CL? How do you find out CL? CL is W by S by Q. Write that properly. Correct? Okay. So you find out 3 CLs. Then what do you do? What do you do next? You need to find out DFS by DQ. DFS by Q by DCL is 0, right? How do you do that? How do you do that? Okay, let me just erase these. Let me just erase these and then we'll make new columns. So let me just make a new set of columns. What do we have to do? Fs by Q. Fs1 by Q. And Fs2 by Q. Correct? Let's try finding out this. You find out this and then you can plot it, right? You can plot it fairly simply. So let's find out this. Fill up these 4 columns. So let's take some time for that. Fill up these 4 columns. Okay, I hope you've all done some of it. So I'm just filling up these values. Verify it with yours, check it up. Maybe mine is wrong. Let me know where I'm going wrong. Okay. These are the values that I've gotten. Please note that we are taking this because the question says pull is positive. Okay. Otherwise, our convention says push is positive. Okay. Okay. So this is 0.001, 0.0001. Okay. Now what do we do? What do we do after this? What should be done? We plot these values, right? So you take a graph. What is it? Fs by Q, and you have Cl here. And you plot these values. How do you plot it? Take the 2 points and plot it. So at point 2 Cl, for instance, you have 0. And at point 4 Cl, at point 2 Cl, what do you have? 1. This is point 2. This is point 4. This is 0.001. 0.001 minus. This is so on and so forth. Okay. So this is point 2. You have that. 2. You also have minus 0.002. Okay. And at point 4, what do you have? Point 4, you have 0.002. So that line goes something like this. And you have another line like this. Okay. So what do? You find out the slope of both the lines and plot that now. Okay. What do you do there? You do this. dFs by Q by dCl versus CG location. So what are the two CG locations? We have 0.2 and we have 0.25. And what are the two slopes? Find the slopes. Can you find the slope? Just find the two slopes. Have you found the slopes? Have you found the slopes? Okay, the first slope, it is this as well. So dFs 1 by Q by dCl is what? What is the first slope? So I've got it as 0.02 and dFs 2 by Q by dCl is 0.001. Plot it and find the neutral point. We'll discuss this question in the next class, okay? We have discussed this in the last lecture. We'll complete this in the next lecture, all right? Okay. And this was the question for your assignment. Let's read the question carefully. Consider the following airplane in prop off condition being tested in a wind tunnel. CG is 30% of Mach. Weight is given as 700 kgs. Aspect ratio of the wing, wingspan, wing mean aerodynamic chord C bar, tail aspect ratio, tail span, A naught. What is A naught? Alpha naught. What's alpha naught? Alpha naught is the angle of attack for zero lift condition, okay, of the wing profile. You have wing setting angle, tail setting angle. You have the lift curve slope of the wing and the tail airfoils, okay. you have the distance between tail aerodynamic chord and CG, that is the moment arm, LT is given 6.5 meters. Elevator area, elevator chord, delta E naught. Delta E naught is for the delta E required equation. Elevator effectiveness parameter tau, then the downward slope, tail efficiency factor, gearing ratio, CH delta E, CH alpha, CH delta T, and CH naught. Look at this, that all the three derivatives, like we discussed, all three of them are negative. What does this mean? That the hinge line is ahead of the center of pressure of the elevator. Okay, all three derivatives are less than 0, negative. Okay, now this is the graph that's given to you in the question. The following CM versus CL curves were obtained for elevator fixed and elevator free case. So which is more stable? Look at this graph and tell me which is more stable. We had discussed this in the beginning of this lecture. Which is more stable? Whichever has more slope is more stable, right? More negative the slope, more stable. So which has the more slope? The fixed elevator case. So this is more stable. And this is less stable. Okay. This we also know from our equations. Okay. Now the first question, find the stick fixed neutral point. The stick fixed neutral point is dash percentage of mean aerodynamic chord. How do we go about doing this? What is the equation for the stick fixed neutral point? If they've given you the slope, DCM versus DCL, they've given you the graph, you can find the slope. Does that give you a clue? So this is the equation. Can you find out? Find the slope, plug it in there, and tell me what the value of X bar NP is. XCG is given to you, right? XCG, yes, 30% of Mach. So XCG is 0.3 C bar. Try to find out the pitching moment and find out X bar NP. Find the slope and then X bar NP. How do you find the slope? For the stick fixed case. This one. How do you do that? You find the slope. You do minus 0.05. Okay. So that is the upper limit. Minus 0 by 0.3 minus 0.8 is equal to X bar NP minus X bar CG is 0.3 C bar. So how much is X bar NP? What is the value? 0.3 C bar plus 0.05 by 0.5. It comes to 0.4. So it's 40% of the mean aerodynamic chord. Correct? Correct. Now the next question, stick free neutral point. The same steps you follow, but for the next slope. How do you do this? Same thing. You have minus DCM by DCL is equal to X bar NP prime minus X bar CG. Find the slope. It's very simple. 0.05 minus 0. Minus 1. Minus 0, right? You have 0.3 minus 1 is X bar NP prime minus 0.3. So how much is X bar NP prime? Can you calculate and tell me? Can you just calculate it? It's very simple. It's very similar to the previous one. We just changed the slope. We just took the slope of the stick free case. Yes, so it comes to 0.3714 or something like that. So 37% of mean error and record. Okay, next question. Find the wing area of the aircraft. How do we do this? What is given to you? Read the question carefully, see what's given to you, what data you can use. Read the question, what data can we use to find out the wing area of the aircraft? Aspect ratio of the wing. So this aspect ratio of the wing, okay, not of the tail. So the aspect ratio of the wing is given to be 6. 6 equals the span, the wing, swing, okay? So 6 equals 6 square by S wing. S wing is therefore 6 meters, meter square. So 6 is the answer. Next question. What is the indicated trim airspeed for stick fixed case? Take density to be 1.225. How do we go about doing this? How do you find trim airspeed? What is the trim condition? Lift equal to weight. Then how do you proceed? We've done this question several times. It's part of almost every long set of questions. How do we do this? Okay. So this is the equation that we know, and we know that lift equals weight, right? So it's basically weight equals 1/2 rho v square SCL, and in this case trim. So this will be trim. So we need to find out the weight trim is square root of 2W by rho SCL. Now W is given to us as 700 kgs. So we have 2 into 700 into 9.81. Density they've asked you to take as 1.225. So you have 1.225 into S. S we just calculated. What was the value? 6. And CL. What is the value of CL? CL is the CL given in the question? Let me just check. Is the CL given in the question? The lift curve slope is given. And just a minute. How did you do these questions? Is the CL given in the question? Okay, CL should have been given in the question. It is CL equals 0.8. How did you do these questions? Okay, let's proceed. So substitute CL equals 0.8. And what do you get? Just plug in the values and let me know. Comes to 48.33. Yes. Let me know if I'm making any mistake. 48.33. Okay. Ask these questions up in the forum if there was any question. Okay, let's proceed. The tail volume ratio VH. How do you do this? What is the formula for volume ratio? Horizontal tail volume ratio. What is the formula? Yes, so you have ST upon S, LT upon C. ST they've given, S they've given, S we have found out. LT they have given in the question, C bar they've given the question. Just directly substitute and find out. ST have they given? No, find out ST the same way we found out S wing. So aspect ratio of the tail is BT square by ST. Aspect ratio of the tail is 4, BT is 2, and ST. So ST is, what is the value of ST? 1. Plug that in here. We have 1 upon S was 6. And T is given to be 6.5. And C bar here, 1.2. So what is the value? Just calculate it fast and tell me. Point 9027. So the answer is 0.903. That is the what tail volume ratio, horizontal tail volume ratio, VH. Okay. Next question. What is the value of Cm delta E? How do you find out Cm delta E? Cm delta E, we have a direct formula, right? Direct formula for Cm delta E minus eta VH Cl alpha tail tau. Now here the Cl alpha tail that is given to you is of the airfoil, but we need to compute it for the entire tail, right? Not just the airfoil. So how do you do that? So we know this formula that relates the 3D and the 2D case. So the 2D being the airfoil, 3D being the tail. Okay. So what you need to ensure here is that all quantities are in per radians or radians. Only then this formula is valid. I had mentioned this several times before. I'm stressing it even now. So it has to be in per radians or radians. Only then the formula will be applicable. Okay. So in the question, they've given you the values in per degrees. Okay. Please convert it. Let's try doing it. How do we do this? CL alpha 3D. So the numerator need not be converted into radians. Why? Into per radians. Why? Can someone tell me why? Because your final answer, you need it in per degrees. Okay, so leave the numerator as such, but the denominator is a non-dimensional quantity. Hence, it has to be converted into per radians. Okay, CL alpha 2D is 0.1, that is per degrees. This is 1 plus CL alpha 2D in per degrees is 0.1. How do you convert it to per radians? 57.3 by pi, E take it to be 1, AR of tail. Exactly. Compute this. What is the value? What is the value? What is the unit? 0.068. What is the unit? Because the numerator is in per degrees, it is still in per degrees. Correct? Now you plug this value in here. So Cm delta E is minus eta. Eta is eta tail. Okay. So where is the value? Is it given? I remember reading it. So it is there somewhere. Can you tell me what the value is? Yes, here it is 0.9. Minus 0.9. What is the value of VH? 0.903. Cl alpha tail 0.068 per degrees. Tau here 0.4. So what is this value? Calculate it. Minus 0.0222. Okay, so this is the answer in per degrees. Okay, it's in per degrees. All right. Next question. If the airplane was to be trimmed at indicated airspeed of 200 km per hour, find the tab setting required in degree for CG location of 20% mean aerodynamic chord. So they've given you indicated airspeed, check the unit. Always check the unit. They're giving you in kilometers per hour. We require it to be in meter per second. Okay. Find the trim tab setting, delta T. What is the delta T required in degrees for CG location of 20% mean aerodynamic chord? How do we go about doing this question? So we have this equation. First, you have to convert the speed. Like I mentioned initially, be very careful of the units. You need to convert the speed. Right. Okay. After converting the speed, you need to use this equation, Fs equation that we had seen in the beginning of the slides, Fs equation. And what does it say? It says trim tab setting. Find the tab setting required at trim, right? Find the tab setting required for CG location. So tab setting required, you need to find out delta T. Delta T is this. Correct? It should be at the trim condition, needs to be trimmed. So what happens at trim? What happens at trim? Stick force is 0, correct? It has to be set to 0. So the tab angle setting at which stick force is 0. How do you find that? Just rearrange those equations, set it to 0, rearrange the equation to get delta T. Now look at this equation, tell me what values are known and what are unknown. W by S, we have W, we have S, we have computed S, right? W is given, S is computed. Next. Density we have, take it as 1.225, density we have. VI, indicated airspeed. Do we have it? Yes, we do. It's given in the question, 200 km per hour. Okay. Next, CH delta T. Do we have it? Yes, it's given directly in the question, CH delta T. Then CH delta E, again given in the question, CM delta E, which is computed. Previous question, we computed CM delta E. Then DCM upon DCL free. Do we have it? No. So we need to find out DCM upon DCL. A, do we have it? No. We need to find out A. And then CH delta T is directly given in the question. Okay. Now let's find out A. Let's begin with A. This is the equation for A, right? Let's try to find out this. Try doing it and then we'll do it together. Try doing it. All the quantities are given in the question as it is. CH naught is given to be 0 as given in the question. So that's 0. CH alpha is given in the question, that is 0.05 into alpha naught minus 2 degrees minus wing setting angle is 0 plus tail setting angle is 2 plus CH delta E is 0.007 into delta E. What is delta E? We had just calculated. To be delta E naught, right? So delta E naught is, how much is it? 3 degrees. Okay. Can you tell me this value? Okay, so A is minus 0.02. Just correct me if I'm wrong. Tell me if I'm going wrong anywhere. Okay. Okay. Next, what the unknown parameter that we have is DCM upon DCL free. How do you find that? We have X bar NP, right? X bar NP prime. You can find that out easily. The slope is given to you. You can just find it. So, but our CG location is different, right? The CG location is different from what is given in the question originally. So, we have to take the X bar NP prime value that we had computed in the first question. Okay, so CG location here is 20%. So it's 0.2 minus X bar NP prime from the first question, 37% of mean error and McCord. So how much is this value? Minus 0. How much is this value? 1714. Okay. Now this A, it is that. This A and this DCM upon DCL free, we have just computed now. Correct? Plug that into this delta T equation, find out the delta T. Can you tell me quickly what is the value? Let's just write it down. So delta T is 2, W is 700 into 9.81 by S. S was 6. Correct me if I'm going wrong somewhere, okay? Into 1 by 1.225 into VI, the converted velocity, it's 55.55. Into 1 by CH delta T, 0.003. CH delta E, minus 0.007. By CM delta E, we had just computed, minus 0.0223. Okay. DCM upon DCL free is minus 0.1714. Minus A is minus 0.02 by CH delta T minus 0.003. Okay, so what is the final answer? Delta T. How much is the delta T required? In degrees. All of these are in per degree, so there is no conversion required. What is the final answer? Compute it and tell me. I'm getting 3.859. Okay, correct me if I'm going wrong somewhere in the computation or the formula or the substitution, just correct me. So 3.85 is what I'm getting. Let's go to the next question. calculate the DFS by DV for CG location of 20% mean aerodynamic chord, same as the previous case. How do we go about doing this? DFS by DV. We have the FS equation. If you take its derivative with respect to V, will we get it? You have the FS equation, right? Take the derivative with respect to V. You should be able to get it, yes? Yes. Okay. So you take the derivative, you find that, right? Where K is given by minus G SCCE eta T. Let's find out K, substitute it there and do it so. DCM upon DCL free. We had just calculated with the previous case. So I'll just do that. DCM upon DCL free is X bar what is it? X bar CG minus X bar NP. So it's 0.2 minus 0.37. So it's minus 0.1714. Yeah. Find out K. How do you find out K? All the quantities are given to you directly. So minus G. G is the gearing ratio. That's 1.5. SE. SE is given to you. Yes. 0.5. CE. Elevator chord 0.25. And eta tail is 0.9. How much is this value? Just plug in that K in the DFS by DV and tell me the final answer. Give me the final answer. Find out K. I don't have a calculator with me. Find out K. So I'm getting minus 0.16875. Plug that into the top equation and your dou Fs by dou V. What is the value? I'm getting something around 0.37. Yes. Are you all getting that? So 0.37, that is the answer. So I think there is no time to begin the next session. That is the week 8 content. So it's fairly simple. All the very best for your assignment date, which is due tomorrow. So if you have any other questions, we can discuss them now. Okay, if there are no other questions, then we can end the session today. So all the very best for your assignment tomorrow. We'll meet again next week on Tuesday. Okay, thank you.